Today is Tuesday, September 1st, and I want to talk about how to do a problem from today's merit worksheet that we did talk about in class, but it got a little messy and it went a little fast. So I wanted to talk about it a little more here so we could clear things up. And specifically, I want to look at number 3, in which we have vectors A and B, and the angle between them is theta. We don't want to assign any numerical values, but we want to start by drawing a line from the head of vector B, this tip of it, down to A so that it meets at a right angle. So I'm going to say it looks something like that. And then label this point where it meets as C. So that's all we have to do for part A. For part B, we want to find the length between 0, 0, which is here at the origin, and C. I'm going to go ahead and for shorthand call that length L. And I want to find it in terms of the vector B and the angle theta. Now, because this is a right triangle, we've got this nice right angle, we've got 3 sides, we've definitely got a right triangle. I can use things like sine and cosine and tangent. In this case, I know the hypotenuse, I want to know the adjacent, so I'm going to use cosine, which is adjacent over hypotenuse, and that should be equal to L over the magnitude of B, with L being the length between 0, 0, and C, and magnitude B being the length of this hypotenuse, the length of the vector B. And then I'm just going to multiply both sides by the magnitude of B to get that L is equal to magnitude B times cosine of theta, that angle between vector A and vector B. For part C, I want to find the unit vector in the direction of A. And anytime I want to find the unit vector, this is not official shorthand, this is just something I write for myself, I'm going to take the vector and divide by its magnitude. And this should be true no matter what I started with. If you wanted the unit vector in the direction of some new vector v, I would do the same thing. I would say v divided by its own magnitude. And let me sort of as an aside verify that this is true. Is this the unit vector in the direction of A? Well, what's its magnitude? If it's a unit vector, it should have magnitude 1. So let me take the magnitude of this. That should be the same as the magnitude of A over the magnitude of A. But since the magnitude of A is already a scalar, when I try and take the magnitude, I really am just saying it's still a scalar. So that's going to cancel out and give me 1. So I do have a vector of length 1. Does it point in the direction of A? Well, I can think of it as 1 over the magnitude of A times A, where 1 over the magnitude of A is a scalar, and then a scalar times the vector A definitely still points in the same direction as A. So I do have a unit vector, and it does point in the direction of A. Now that I have a unit vector in the direction of A, I want to use that and part B to figure out what the vector, I'll call C, from 0, 0 to the point C is in terms of A, B, and theta. So I know from part P that that vector should have length, magnitude of B cosine theta. And I know based on the fact that C is lying along this vector A, C should point in the same direction as A. It shouldn't have the full magnitude that A has. It should only have magnitude B times cosine theta, but it should still go in the same direction as A because it lies between 0, 0, and A. So I'm going to say I want it to point in the direction of A. I'm going to take the unit vector in the direction of A so that I'm not interfering with the magnitude at all. I'm just pointing in the right direction, and now I need the magnitude, and the magnitude should just be the length from 0, 0 to the point C. So I'm going to plug that in to be magnitude of B cosine theta, and maybe I'll rewrite this, I think I will, as magnitude B over magnitude A cosine theta, and then all that in the vector A. So this part is telling me my magnitude, this part is telling me my direction, And that's all I need to know for a vector. As soon as I have direction and magnitude figured out, I should be good to go. And again, just to highlight, this part of C was giving me my direction, but not contributing to the magnitude because it only had magnitude 1. So whatever I multiply it by, it will take on that magnitude. And so then I multiplied by the appropriate length between 0, 0, and C to give it the desired magnitude. So now I know what the vector C should be in terms of A, B, and theta. And for D, we want to use the dot product to solve for cosine theta to just leave everything for C in terms of A and B. So recall that the dot product A dot B is equal to the magnitude A times the magnitude B times cosine theta for theta, the angle between them. And to reverse solve, I'm going to divide both sides by magnitude A, magnitude B, so that I get cosine of theta is equal to A dot B over magnitude A times magnitude B. And then I'm going to plug that in. I had that C was magnitude B over magnitude A times cosine theta, but now instead of cosine theta, I'm going to use A dot B over magnitude A, magnitude B. And then I still have this factor of in the direction of vector A. We can simplify this a little. In particular, I've got a magnitude B up top and, sorry, magnitude B down bottom, and I also have one up top. So those will cancel out with each other. And I should be left with A dot B over magnitude A squared times A, which is also the same as A dot B over A dot A times A, which is also the same as A dot B over magnitude A times A over magnitude A. So you might see in these different ways. I'll jot down up here, talk real quick about why A dot A is the same as magnitude A squared. Again, by the definition of dot product, A dot A is equal to the magnitude of A times the magnitude of A times the cosine of the angle between A and A. The angle between A and A is 0, they're identical. And the cosine of 0 is 1, so that leaves me with magnitude A squared. Okay, so I get any of these are correct because they're all equal to each other. You might see any of them, though, as being the formula for projection. So depending on if you're looking at the textbook or the lecture notes or the lecture video, or if you're looking at an outside source, these are all considered valid formulas for projection. And so is this the same as the formula for projection? Yes. Now, why is that true? Well, remember that projection is supposed to be measuring, we think of it sort of as casting a shadow. So it does make sense that this new vector C that only goes from 0, 0 to the point C is sort of the shadow that B casts onto A. We can also think of projection as the amount that B goes in the A direction. So how much does this vector sort of agree with this vector? It goes this much and then no further in the A direction. Yeah, I think that's all I have to say about this one. It makes sense for this to be the same as the vector, as the formula for projection, because this is literally exactly what it's calculating. And so if you see a question that's asking you for the projection and you're having trouble visualizing it, think about casting the shadow, think about finding that leg of the right triangle. Think about how much does the vector B go in the direction of vector A. Incidentally, that is what this is asking for. If I see projection of B onto A, that's how I want to be reading it. The little vector is the one that I'm projecting onto. It's also the one that pops up the most times in the formula. A really has all the power. A decides what direction you're going to go. B contributes a little to the magnitude. So this does give us the formula for the projection of B onto A, no matter what form that formula takes. And I think that's all I want to say about this problem. Feel free to reach out if you have any questions. You can post to the CampusWire page for our class, or you can send me an email, or you can just ask at the beginning of class next time. All right, see you later.